So in continuation of the problem solvings by section method, we can see here the second example. So this example was asked to do as your assignment. So first of all, in order to solve this assignment or solve this problem, let's read the question first. Determine the following items, which is axial force, shear force at B, bending moment at just left of B, axial force, shear force and bending moment at F. So in order to solve this problem, the first step you need to do is that you need to draw the free body diagram. In order to draw the free body diagram, firstly you need to replace the support with the reactions. So we can see here pin support and a roller support. So pin support will be replaced by two reactions and roller support will be replaced by one vertical reaction. So using the equation of equilibriums, we can easily calculate the reactions that was taught in your previous lecture. So the vertical reaction at A will be 1 and vertical reaction at D will be 8. We will be solving this or calculating this reaction using the equation of equilibrium, which is summation of f of x equals to 0, summation of f of y is equals to 0 and summation of moment equals to 0. So using these three equations we can easily calculate this reaction. So firstly we need to calculate this reaction, then we will have to take the section that we are asked to do. So in this first part we are asked to calculate the axial force, shear force and at B. So we need to consider a section at B. So taking a section at B, we can see that there is a vertical reaction. As we are asked to calculate axial force and shear force at B, so we don't need to consider this moment at first stage. So we are not considering the moment here, then all other will come except the moment. So we have considered the vertical reaction. Now let's denote it with the conventional axial force sign and shear force sign. So as we have taken the left section, the shear force will be positive in downward direction and axial force will be positive in tension. So we have denoted with it with vertical shear force, axial force and a moment. So at second portion we can see here that we are asked to calculate the bending moment at just left of B. So as it is asked to calculate the bending moment at just left of B, we haven't taken this moment. We have avoided this moment as we are asked to calculate the moment at just left of B. So we can see the moment is exactly at B. So as we are asked to calculate the moment at just left of B, so we haven't included this moment. So other than that, we have introduced the conventional signs. According to the conventional signs, we have introduced shear force, axial force and moment that we need to calculate. So using the equation of equilibriums, now we will be calculating shear force, axial force and bending moment. So let's do it. So using summation of f of x equals to 0, we can see here that in this portion AB segment only axial force is P, or only force in x direction is P, which is in positive, as we have considered rightward as positive. So only P and the value of P will be 0 as the summation of f of x is 0. Up next we need to apply summation of f of y. So applying summation of f of y and considering upward direction as positive, we will consider all the y directional forces here in order to form this equation. So we can start from point A. In point A or at point A we can see a 1 kip load acting upward, so it will be positive 1, and then we can see another y directional force which is acting downward, V. So as we have taken positive in upward direction, so it will be minus V. So in total it will be equals to 0 according to the equation of f of summation of f of y is equals to 0. So from here we can calculate the shear force also. V is equals to 1 kip, which will be acting downward. Actually you don't need to um, put the sign here, you can avoid the sign. Only as we have already shown this in figure that V is acting downward, so you don't need to write it in your answer the direction. You can avoid the direction in your answer. Up next, applying summation of moment, we can easily calculate the moment. So we need, as we are asked to calculate the moment at just left of B, so taking moment at just left of at this B point, we can see that apply and considering clockwise direction as positive. So this 1 kip load is creating a rotation. This 1 kip load is creating a rotation in this direction, which is clockwise, and we have considered clockwise as positive, and this distance to point B, perpendicular distance to point B, will be 3 feet. So the moment will be 1 into 3, and as it is creating a rotation in clockwise direction and we have considered clockwise direction as positive, so it will be positive 1 into 3. So other than that, we can see here shear force V and axial force P. These two doesn't have any perpendicular distance from B point, that's why these two will not give any moment, but we can see that at B point there is a moment. So we will be considering this moment. This moment is acting anti-clockwise, that's why we have plugged the negative sign, and it will be negative m. So in total the summation of moment it will be 0, so we have plugged here 0. So from here we can calculate the moment also. So in this way we will be calculating the shear force, axial force and bending moment, and in this last part we are asked to calculate the axial force, shear force and bending moment at F. So there is a confusion among some of you guys that how we will be taking the section and how we will be calculating the load in this case. So let's take the section first. We need to take a section at F, which is 2 feet from point C. So taking this section, so we have taken this section. So now we can see that this uniform, that this varying load acting from C to F, acting from C point to F point, is having a base of 2 feet only. So but in the question mentioned in the mentioned question, we can or in the mentioned figure we can see that the total base is 3 feet. So as the base was 3 feet, or when the base was 3 feet, the load acting, or we can consider it as height, as the loading pattern is just like the triangular section. So when the base was 3 feet, the load acting was 2 kip per feet. But as we have taken or considered the base as 2 feet, taking a section at point F, so now this maximum load won't be the 2 kip per feet, it will get decreased. As we have taken the least as we have decreased the base, so the maximum load will also be decreased. So this decreased amount of load, or this new amount of load, can be considered as X. We still don't know what is the value of X. Suppose we are considering X kip per feet. So considering X kip per feet, now let's calculate the value of X. So we can do it in several options, but I will be preferring to apply similar triangle rule. So using similar triangle rule, we can see this in this figure. So in the mentioned question, the base of the triangular load, or the uniformly non-uniformly distributed load, or we can say it as varying load also, as it is varying. So in this varying load, initially it was 3 feet. So when the base was 3 feet, the maximum load was 2 kip per feet. But as we have taken the section at F, the base was decreased to 2 feet. So the 2 kip feet will be changed. We still don't know this the value, so we are considering it as x kip per feet. Now we need to calculate the x kip, the value of x. So in order to calculate the value of x, we'll be applying the similar triangle rule. So if we want to consider this triangle as a inside triangle of this larger portion, so considering these two as the same triangle, we can see that this is the larger triangle where the height is 2, but inside that there is a small triangle. This is the small triangle. We have considered the height of small triangle as x. The base of the larger triangle was 3 feet, but the base of the smaller triangle or the inside triangle has reduced to 2 feet. So we know the base of smaller triangle, we know the base of larger triangle, we know the height of larger triangle, but we don't know the height of smaller triangle. So we can apply the similar triangle rule here. That means x, which is the height of the smaller triangle, divided by the height on the base of the smaller triangle. So height of the smaller triangle divided by the base of the smaller triangle, which is 2, is equals to height of the larger triangle, which is this 2, divided by base of the larger triangle, which is 3. So from this, so by applying this similar triangle rule, we can easily calculate the value of x from here. So the value of x will be 1.33 kip per feet. So from in this way we can calculate the amount of maximum load, or we can calculate the amount of varying load acting on this 2 feet portion. So it will, the value of x will be 1.33 kip per feet. So in total the value will be half into, so the total load acting here will be half into 1.33, as we have calculated the value of x as 1.33 into base, which is 2. So from this we can get the total load acting from this portion. So we can see here 1.33 kip per feet. Then from 1.33 kip per feet, the total load will be half into base, which is 2, and the height 1.33. The answer will be, if 2 and 2 will be cancelled out, so the answer will be 1.33 in total. So 1.33. So this 1.33 will be acting at a distance of 1/3 of its base. So now we have taken the base as 2 feet, so 1/3 from this point, 1/3 from the larger point, and 2/3 from the smaller point, smaller side. So as this is the larger portion, so from here the distance of the centroid where the load will be acting will be 1/3 into base, which is 2 feet. So here the answer will be 0.667, 0.667. So we have already calculated this. The answer is 0.667 or 0.66. We can consider the first 2 digit after decimal. Now we need to denote the conventional signs, denote with the conventional signs of shear force, axial force, and bending moment. So we had denoted these 3. Now we will be calculating these 3 using the equation of equilibriums. So firstly, applying the summation of f of x equals to 0, we can see that only x directional force is P, which is acting rightward, and rightward, as we have considered rightward as positive, so the value of P will be 0. and after that applying summation of f of y is equals to 0. So starting from point A, we can see 1 is acting upward, so this is positive 1. So up next it is moment, so it will be considered, as we are considering y directional forces only. So 1.3 which is acting downward, so minus 1.3, and next v is acting downward, so minus v equals to 0. From here we'll get the value of shear force, and at last applying summation of m is equals to 0. So as we are asked to calculate bending moment at point F, so we have taken summation of moment at point F equals to 0, and we have considered clockwise as positive. So starting from point A, this one reaction is giving rotation at clockwise direction, so we have considered clockwise as positive. 1 into total distance from point F is 8. You can see 3 plus 3 plus 2, which is 8, so 1 into 8, and it is positive as the rotation is clockwise. And then we can see here a moment, so it will be included as we have taken the summation of moment, and this moment is acting anti-clockwise, so it will be negative 24. So we have considered negative 24, and at last not the last one, but 1.33 into 0.667, so it is also acting anti-clockwise, so it is negative 1.33 into 0.667, and at last we can see a moment here also, so this moment is also acting anti-clockwise, this will be minus m. So from here we can calculate the total moment. So in this way we'll be calculating the shear force, axial force, and bending moment, for example, for this section up to point F. Thank you. Now in example 3 we can see that we are asked to determine the axial force, shear force, and bending moment at E. This is easier one, but the one thing is that here we can see a fixed support and there is no other support. As we know that this is a fixed support, in order to draw the free body diagram, this fixed support will be replaced by 3 reactions. One will be in vertical direction, one will be in horizontal direction, and one will be moment. So replacing this fixed support with 3 reactions, let's see, we have replaced this fixed support with 3 reactions, and now we are asked to calculate shear force, bending moment at E. So before that we need to calculate the reactions first. So in order to calculate the reaction, first we need to simplify the load. We can as we can see that 8 kilonewton load is acting, which is inclined, and it is 30 degree with the horizontal, so this will be the cos component, 8 cos 30, which is 6.93, and this one will be the vertical component. The vertical component will be the sine component, so this vertical component will be 8 sine 30, which is 4. So from here we are replacing the inclined load with 2 components, and now we can see here a uniformly distributed load along a length of 4 meter. So in total this load will be 2 into 4, which will be acting just at the middle portion of this uniformly distributed load. So total load will be 2 into 4, which is 8 kilonewton. 8 kilonewton. It will be acting right at the middle portion, or right at the midpoint of this 4 meter, which is at a distance of 2 meter from D and at a distance of 2 meter from E. So now first thing we need to do is that we need to calculate the support reactions, which is our initial step for each and every method, which either it is section method or diagram method. So let's calculate the reactions first. So in order to calculate the reactions, we will, as earlier we have already seen that we used to apply equations of equilibrium, so we are doing the same here. We are applying the equation of equilibriums in order to calculate the reactions. So firstly, applying summation of f of x equals to 0, we can see here that, and considering rightward direction as positive, we can see here that in this entire beam the x directional forces are 6.93 rightward, so that's why positive 6.93, and dx in rightward direction. There is no other x directional forces, only these two. So from here we can calculate the value of dx, which is minus 6.93. And next, applying summation of f of y. So here we have applied summation of moment first, but it's up to us. We can apply summation of f of y first. So, applying summation of f of y, we can see in this entire beam 4 kilonewton is acting downward, so minus 4, 8 downward, that's a minus 8, and dy upward, that means plus dy. So from here we can calculate the value of dy, which is plus 12, and at last applying moment, which is summation of moment. So we have considered moment at D point. So at D there will be a moment, and as this is a fixed support, there will be initially there will also exist a moment which we have denoted with MD. So taking a moment at D point, we can see that the forces or loads which will give moment or induce moment will be for keep 8 kilonewton and this MD portion. So applying summation of moment at D equals to 0 and considering clockwise as positive, we can see this 4 into 6 will be creating a rotation in anti-clockwise direction, but we have considered clockwise as positive, so we will have to write minus 4 into 6. Next we can see 8 into 2, this is also creating a rotation in anti-clockwise direction, that's why minus 8 into 2. And at last this MD, this is also in anti-clockwise direction, that's why minus MD. From here we can also calculate the moment MD. And at last, as we are asked to determine the axial force, shear force and bending moment at E, so like the previous examples, we'll have to take a section. As we have already calculated the reaction first, then we need to take a section at point E. So taking a section at point E, just at point E, so we have taken a section at point E, that means the length of the uniformly distributed load will get reduced. So initially it was 4 meter, now it will, as we have taken at point E up to E, the length will be 2 meter. So we will have to consider the length of the uniformly distributed load as 2 meter. So as this is 2 meter and the load acting is 2 kilonewton per meter, so the total load will be 2 into 2, which is 4, and this will be acting right at the middle portion, which is 1 meter from point E. So we have taken everything, each and everything at left of E, and we have taken this section up to E, and we have considered everything up to E. So now we'll have to denote with the conventional sign or the directions of axial force, shear force and bending moment as well. So denoting with shear force, axial force P and bending moment M. Now we'll have to calculate these three things. So in order to calculate these three things, we'll have to apply the equations of equilibrium. So using the equations of equilibrium, we can easily calculate the value of axial force, shear force and bending moment. So in this way we'll be solving the problems with section method, or we will determine the internal forces with section method. This was all for lecture 3. Thank you.